So, this video will be focusing on using all of Newton's third laws for different types of situation. And over here, what I have are a few scenarios that you might see on the AP exam and how to approach it. So let's start off with number 4. Now, number 4, it states, a block with mass of m is at rest on a region of rough surface with a static coefficient of friction 0.4 and the kinetic coefficient friction of 0.3. A force of 2 times the weight of the block was applied to the block. Does the block accelerate? Justify your answer. Okay, so let's just draw the scenario right here. So where's my mouse? There it is. I'm gonna get a pen. Okay, I guess we're gonna do it in red. I thought I asked for black. Yeah, there you go. Okay, so we have a rough surface, right? So, that's it. We asked for a rough surface, so this will be our rough surface right here. Okay. Now, there's going to be a block with the mass m, right? And a force is being applied to it, right? So I'm just going to draw a force vector. Right? This is the force of the push, right? So this is our diagram right here. Now the question asked us, does a block accelerate, right? So number A is asking accelerate. Does it accelerate? Right? Now, first of all, any kind of physics problem, you always want to visualize or even draw down the force body diagram, right? And that covers all the forces, not the components, but just the forces. So in this case, there is the weight, right, and the normal force from the ground, right? So this is force of normal and force of gravity. Or in this case, it can just be mg, right? Because force of gravity is just the mass of something times the gravitational acceleration, right? And remember, the question says that a force 2 times the weight of the block was applied. So what we need here is that we need to realize that a force of 2 mg was applied, right? Because if it's 2 times the weight, which is in this case it's the gravitational force on the block, right? Then really double that is just basically 2 mg's, right? Or you can notate it as 2 fg, 2 mg, whatever the case is, so long as you're saying that the force applied in the right direction is 2 times the amount of its weight, right? And of course, there is friction, right? But we don't know what that friction is, right? We don't know whether it is equal magnitude or less magnitude, right? But we do know for certain that there is a force of friction on it. So, to determine whether there is an acceleration, what we have to consider is this formula. Newton's second law, which is force equals the sum of all forces in one direction, right, equals to the mass times acceleration, right? To say that something accelerates, you are saying that there is a net force in that direction, right? In this case, we are focusing on the left and right direction, right? So the only forces that are taken account of, right, in the left and right direction is the force applied or the force of the push, which is 2 mg, right? 2 mg. And we're trying to decide whether there is a net force, right? So in this case, we have to figure out what the magnitude of this frictional force is, right? And according to, I think you already guys learned this, is that the frictional force is equal to the mu, the static coefficient of friction times the normal force, right? Now, remember, when you're trying to determine whether something accelerates, right, you have to ask yourself whether the force applied to that object exceeds the static friction of the block, right? Because if it doesn't, then that means the block isn't accelerating, right? Like you can grab any kind of object like this water bottle right here. you set it on any surface, right? And you can apply a force to it, right? And it moves, right? I'm applying a force to it and it moves like this. But if I apply a force that is less than the frictional force, right, then what's going to happen here is that it's not going to move, right? Because the force that I'm applying to the object is not greater enough to overcome that frictional force, right? So the first thing that we want to do is decide whether that 2mg is greater than this, right? So let's set this comparison up. The 2mg is it greater than the static friction, right? Does it? Well, let's see. So we have to determine what mg is, right? Actually, hold up. Actually, we can decide here is that the normal force is actually mg, right? According to our force body diagram, right? And of course, you just basically algebra. So cross that mg out, and we can see here that 2 is going to be greater than the static coefficient of friction. Is that true? Well, the problem says that the static coefficient of friction is 0.4, so yes, it is true. The block is accelerating, and we did justify our answer. Right? Now on to part B. I'm just going to erase some of these stuff. Now that we know that it's accelerating, part B states, draw the force body. Oh, wow, we already did it right here, right? So we already draw the force body diagram right here, but let's actually correct it. Instead of saying that the frictional force is equal magnitude, we're actually going to write that the frictional force is actually a little bit smaller than the force applied, right? The force that is 2 times the amount of its weight, right? Based on the problem. So this is the correct force body diagram, right? So part B is done unintentionally. So next one is to determine the block's acceleration during the moment the force was applied to the block, right? The block acceleration. Okay. So again, always think about this equation right here. Remember, we already know that the force of the push is greater than the force of friction, right? The static coefficient of friction. Therefore, there has to be a net force along the x-axis, right? So let's notate it. So 2Fg minus the frictional kinetic friction force, right? Because we're specifically talking about the kinetic friction, equals to m, oh, that's a sloppy m, there you go, m and a, right? And then from there, we just solve it algebraically. So in this case, f of g is the force of gravity, and we notate it as mg, 2mg minus, well, friction is equal to the the coefficient of friction. In this case, it is the kinetic, times the normal force. In this case, it is mg. So put those two together, you get mu k, subscript of k, mg, would equal to ma. Okay. Now, you see here the m's are in both equations. So what we can do is we can cross this out. And we're left with, right, 2g minus the kinetic coefficient of friction times gravitational acceleration would equal to a. Right? And let's make sure that there's no other requirements, just that. Yeah, so that is the acceleration of the block, right? Now, I think it was after the push was exerted. Okay, so yeah, so C was during at which the block was being pushed on, right? So this is the acceleration that goes for letter C. But now letter D, it states that what is the acceleration after the push, right? So this is what's going to happen here. Let's get an eraser. Let's open the speed. Let's erase this part. Now what's going to happen after the push is that the push, the force of the push won't be there anymore, right? And what's going to happen here is that actually our force body diagram is actually not going to change that much. the only thing that you are removing is actually just the force of the push, right? So in this case, everything else stays the same. The force of normal equals to mg, which is the gravitational force acting upon the block, and of course, force friction, right? The frictional force, and more specifically, this is the static coefficient, or using the kinetic coefficient friction. Yeah, there you go. And that is basically our new force body diagram, and I'm going to specify this is after push. This is after the push, right? Now, you can see here that the only thing that is contributing to, right, the acceleration after the push is that frictional force, right? So again, notate your second law from Newton. Sum of all forces in one direction equals to the mass times acceleration. So the only thing that is leading that acceleration, or is the result of this net force, is F, right? Friction would equal to ma. Okay. Now, friction force, right? And this is the object is moving, so it's going to be mu k, and then normal force, which is mg, equals to ma. Cross that out. M's canceled. Then what you have here is that acceleration would equal to mu k, right? The kinetic coefficient of friction times gravitational acceleration would equal to a. And of course, you can solve it for yourself right here. It is 0.3 times 9.8. So I have a calculator with me. So I'm just gonna use my phone. 0.3 times 9.8. The acceleration is approximately 3 meters per second squared, right? Always use your units. Always use your units. Meters per second squared, right? Now, we go on to the letter E. It states that the same experiment was run, but this time the block is now traveling in a smoother surface. Would the magnitude of the acceleration increase or decrease? Okay, so a little bit of a little insight towards frictional force and all. The rougher the surface, right? The rougher the surface. That's not rough. ROUGH. If you increase the roughness of the surface, what you're essentially saying is that you are increasing the frictional force, right? That's what friction is, right? Friction is basically the resistance of the direction an object is moving because of the roughness of the surface, right? And the only way to increase the frictional force is by increasing the coefficient of friction, right? Whether that is UK or US, the static coefficient of friction or the kinetic coefficient of friction. What matters is that as you increase roughness, you increase the frictional force, right? So if you're making a surface more smoother, then what's going to happen here is that you are decreasing roughness, right? You are decreasing the roughness, right? Roughness, OUG, roughness would equal to decrease in friction, which therefore decreases the static coefficient of friction and the kinetic coefficient of friction, right? So if you're going to have a smaller number, then what's going to happen here is that your acceleration, right? Your acceleration after the push, right? Remember, this is after the push, is going to decrease, right? So acceleration is going to decrease after the push, right? I should have specified it in the part E about what acceleration was, but what E is talking about is basically the acceleration after the push. So yes, after the push, the block decelerates and comes to rest. Determine the instantaneous velocity after the push. Okay, again, this is just a basic kinematic equation, right? So we are assuming after the push decelerates to stop, right? So what's going to happen here is that, remember, our acceleration still remains the same, right? It's a constant deceleration, actually. So therefore, because it is a constant acceleration, right? And it is a one-dimensional motion that we can use kinematics, right? So it asks us to find the instantaneous velocity after rest, but we don't have time, right? And because of that, we can only really use one equation. Is that v final square would equal to v initial square plus 2a, right? The acceleration times the distance that it has traveled. The distance it has traveled, and I'm making sure that there is no other. Yeah, okay. Yes, so this is going to be it. Now, what we have here is, we know that's going to come to rest, so this thing is going to cancel out. We're going to have 0 equal to v initial square, that's what we're trying to solve for, 2 times the acceleration, remember, it is the kinetic coefficient of friction times the gravitational acceleration, right? So mu to the subscript of k times g times the displacement of x, right? Now, let's try to get this number by itself. Okay? So what's going to happen here is that we're going to just algebra simple. Mu k g times by displacement, right? And then square root equals to v initial. And yeah, okay, so immediately you can see here that, you can't take a square root of a negative number. And here comes where, the intuition comes in mind, is that this g, right, this g right here is technically a negative 9.8 when you're specifying which direction it is. So really, we don't care about whether, whether this is a positive or negative, so long as we have the magnitude, right? Whatever this magnitude is inside this radical, that tells us what the velocity is, right? But you see anything that is wrong with this answer? Well, the question says determine the instantaneous velocity after the push, but we don't have a defined variable for the distance, right? We have a gravitational constant, right? The gravitational acceleration, and a mu, which we can just substitute in. But we don't have this variable. So we need to find a way to substitute that variable for something else. Well, this is a kinematic equation after all. Let's solve for that, right? So we know that displacement is going to equal to Vxot. Actually, we can't use that. Okay, let's see here. Let me see what kind of equation we can use here. Kinematic equation. I don't have it with me, so let's see here. Okay, so it looks like I don't think you can find a way to solve for displacement if you don't. Well, actually, yeah, because you don't have time here. So okay, that's fine. So I'm just gonna define this scenario right here. So force of 2 times the weight of the block was applied to the block, right? So after the push, determine the instantaneous velocity. Let me see here. After the push, the block decelerates and come to rest. Travels a distance of d. Right? There you go. So now what we can do is that we can actually start something. So in this case, there you go. In this case, we are not concerned with this negative, right? Because what we do is that we know that this negative 2 will be solved by multiplying negative 9.8 here, right? But let's see. the mu, right? In this case, the mu is going to be the mu subscript k, so kinetic coefficient of friction is 0.3. 0.3 multiplied by negative 9.8. See that? And then multiply that also by distance d, right? And let's say that the distance d, let me just travel a distance of, let's say 10 meters, right? So 10 meters. Distance of 10 meters, and then it comes to rest. So instead of writing d, we can just write 10. There you go, 10. Then we can solve for the initial velocity that it had. 2 times 9.8 times 10, right, times 0.3, and then take the square root of that. Flip phone. Oh my gosh, flip, please. Flip the phone, there you go. The square root of this is going to be around 7.68 or 7.67 meters per second. And that's your answer. Okay, so that is basically our introduction to friction, right? And then we're gonna step up just a tiny bit, and let's do number 1. Just number 1. Yeah, maybe number 1. Actually, you know what? Let's do number 3, because number 3 is kind of difficult. I really want to do this because it's kind of like the review that some of you guys showed me. But okay. Scenario is a block with mass capital M is at rest on a rough surface with a coefficient of friction notated like that. It is also hooked onto a pulley with a massless string. In addition, another block with mass little m is attached on the other side of the pulley. So let's draw this scenario out. Okay. Come on. There you go. So bam, bam. Okay, here it is. Bam. Go and down. This is going to be a little m, and this is going to be big M. There you go, big M. So this is the configuration that we're going to be dealing with as we're doing number 3. So the question A, it says draw a force body diagram of both blocks after the system was released from rest. They do not include components of force. Okay, so let's notate this right now. Okay, I don't know what happened there, but this is for mass capital M. So what we're gonna have here is sorry, we didn't have the rough surface. Let me just make that indication very noticeable. There you go, rough surface. So what's gonna happen here is that, assuming that the acceleration is gonna go down the line, right? Then what's gonna happen here is that the tension force. That's not. You make that a little bit longer. The tension force is gonna pull on here, right? And of course the gravitational force would be down here, which is mg, right? Mg or F subscript of g, however way you want to notate it, and of course an equal magnitude of the normal force, which is F of n, right? Force of normal. And of course we have the rough surface, right? Now remember, this is just intuitive stuff, but friction is always going to be smaller than normal force because of that coefficient of friction. So therefore the arrow has to be smaller, just slightly. This is friction, and that is the force body diagram. Now for the little m, right, the mass that is hanging on the other side, there's only 2 forces that are acting upon it. And okay, so just a heads up, this tension, this tension is pulling on the same amount of magnitude as it pulls on M and little m, right? So what that means is that this arrow has to be the same on big M or little m. So in this case, I'm trying to make sure that they are matching in length to the best of my abilities. And there you go. So this is going to be the tension force that's pulling up on mass M. Now, because it's accelerating down the line, right? That means that the gravitational force of mass M is going to be greater than the tension force, right? Greater than the tension force. This is going to be mg. Remember, this is capital MG. There you go, capital MG, and this is low mg. So this is our force body diagram. Cool? Cool. Now the question says that determine the acceleration of block after M is being removed, or M is released from rest. Okay. And it has to be in terms of physical constants like G and defined variables like the mass, both of the masses, pretty much. And of course the coefficient of friction. Okay. Now, let's do this. So in this case, for the capital M, the only way, right, the only direction that it is really accelerating in is the x direction or the horizontal direction. The only forces that are contributing to that is tension to the right and the friction to the left, right? So in this case, how we want to do this is, first of all, we got to state that there is a not frictional force, but a net force in the x direction for, in the case of big M, right? The massive big M. Now, the net force for the big M in the x direction, we have tension, right? And the reason why that I write tension first is that if this the acceleration tells us which the sum of all forces is going to be in, right? So in this case, we know that tension is going to be greater than the frictional force. And that's why I put tension first instead of friction, right? Because tension is going to be the greater force than friction. So that's why I put it there. Frictional force would equal, to, actually, the mass of the object, which is just big M, times the acceleration. Now, of course, we need to obviously get it in terms of our gravitational constant. But as of right now, we know that the tension minus the friction over the mass of big M would equal to acceleration. So now we need to find a way to get rid of this tension and this frictional force, right? So let's get rid of tension. Let's go actually solve for tension over here. So we can see here that, again, the only direction that this little m is accelerating in is, of course, the y direction, right? So we're going to try to solve for tension, okay? So again, if it's going to go this direction, then the biggest forces that are contributing to that is the gravitational force. So therefore, I'm going to write mg first, right? The gravitational force of this minus tension would equal to the mass of the slow block, which is m, times the acceleration. Now, what's going to happen here is that I am going to get tension alone, right? And I'm not going to show you the entire thing because you guys can do it by yourself, but it's going to basically be mg minus ma, right? Because when you subtract it here and then you flip the signs, it's going to be, like that. So this is going to be our tension, right? Now, what we're going to do is we're going to substitute that in there, right? So bear with me. Tension, right, which is what we found out here, is little mg minus little ma, right, minus frictional force. Now, the frictional force, remember, it's is the kinetic coefficient of friction times the normal force. In this case, it's the big mg, right? So kinetic coefficient of friction times the mass times the gravitational acceleration, that is friction, over, that's a bad line, over m, right? Big M would equal to A. Okay. Now, I just need a little bit more room here. I'm gonna erase some of these because we don't necessarily need them right now because we already did it. So, what we found out is this equation right here. Now, of course, what you wanted to know is that the acceleration of both the masses, right, is equal to each other, right? They are equal to each other. Keep that in mind. And the acceleration of the system is also equal to each other. So I'm going to show you another way that you can solve this, but for right now, let's just solve for A, okay? Now, of course, in your math or any kind of equation that you're going to deal with, you always want to get the unknown variables on one side. So what's going to happen here is I'm going to multiply this big M on this one side so that we can get rid of that stupid fraction. So I'm going to have this expression right here. There you go. We have this expression right here. And what's going to happen here is that we're going to get this MA to this side. So mg minus the mu, kinetic coefficient of friction times, of course, the mg. And what you have here is A times big M plus A little m, right? And of course, you factor it out and then, factor this out. Then divide this term on both sides. And what you get here is that the acceleration of this big M, right? This big M, mass of capital M, is mg minus mu, our kinetic coefficient of friction, times m, big M, g, over m plus m. Okay? Now, I'm going to show you I would say the most easiest way to find this, and it's not going to be a time consumer. Okay, so this is your acceleration. It is the acceleration, but there is a better, more easier way to understand this. Okay, and I don't think the physics teacher have ever taught you this, but at least from in our school at Adobe. But this is how we can find the acceleration without doing the whole substitution thing and drawing those force diagrams. Like, no, this is going to be the easiest way. So there is this formula called the external force would equal to the total mass times the acceleration of the system, right? This is the system right here. This is the system equation, dare I say. Because the reason why that we're interested in the system is because the acceleration of the system, right, would equal to the acceleration of both the big M and the little m, right? Now, what the formula basically is telling us is that the only way that a system can accelerate is if a external force is acting upon it, right? Now, what I mean by external force is that forces that are only contributing to the acceleration of the system, right? So, like this tension force that is pulling on M and little m is not an external force. And the reason why is that both of them are shared together, right? Both the tension forces pulling M and little m with the equal magnitude. And because of that, right, according to Newton's third law, it is considered a equal opposite force, right? In other words, it is considered an internal force, right? If I remove that tension out of the equation, right, it does not change the idea that both m and little m are going to accelerate at the exact same speed, or they will accelerate at the same meters per second squared, right? And because of that, what we're going to end up with is the only forces that is contributing to the system is not tension, but really the weight, right? The weight force of M and the frictional force of big M, right? Because if you think about it, when the big M is moving, the only thing that is being resistant, right, is resistance to this acceleration, is the friction force. And if you, in the case of little m, the only thing that is really wanting the system to accelerate, if you can put it that way, is the weight or the force of gravity acting upon little m, right? Little m mass little m, right? And because of that, then the force external, right, is the weight of little mg, which is mg, minus, right, because remember, friction is resisting the motion, mu to subscript k, kinetic coefficient of friction, times mg would equal to the total mass, so m plus m, get A alone, and look at that. The acceleration of the system is the exact same acceleration as the one that we just found, right? And this makes sense, right? The acceleration of the system has to be equal to acceleration of the individual blocks in this case, right? Maybe in a special occasion or a special rare instances where it doesn't equal to that. But for now, you can see here that the acceleration of the system does equal to acceleration of mass m. And that's a little intuition thing that you must know also, is that the acceleration of the system is equal to acceleration of the objects, right? Because it doesn't, yeah. Like, this is basically a true statement right here, is that whatever the case may be, is that the acceleration of the system must equal to the acceleration of the object. And I spell objection. I'm going to erase that, but you get the idea, right? So that's just a little quick, easy trick to doing these stuff. But anyway, the question then says, determine the time it takes for velocity m to travel to 8 meters in terms of physical constants and defined variables. Okay, so it's talking about time, right? So again, I'm just gonna, where's my eraser? There we go. So we're going to, because this is one-dimensional and it is a constant acceleration, we're using kinematics, right? Right. And make sure that you guys written this down. So I'm just gonna erase these. Yeah. So this is going to be a simple kinematic equation. So they said that the block has traveled 8 meters, right? 8 meters, and you want to determine how long it took them to do that. So just find a kinematic equation that includes time and all your essential material or essential variables. So I chose this one. Displacement, right, would equal to the initial velocity times time plus 1/2 times the acceleration times time squared. Now again, the initial it is released from rest. So again, we don't care about that. What we care about is this grouping right here, and we want to get time alone. So again, I'm not gonna solve for we're not gonna baby feed you into how to algebra it, but the time, right? The time should be this. My bad. It's supposed to be a square root symbol. There you go. Would equal to this. And that's going to basically be time. Now, of course, acceleration isn't defined, and we do have an actual number for the displacement, which is basically 8, right? It's 8. So 16 over the acceleration, but the acceleration, right, we actually solve for, right? Remember, the acceleration, I'm just going to write it on this side, is basically the weight of m minus the frictional force on big M, right, over the sum of both masses, right? That is the acceleration. And we can plop that into this equation right here. So what time ends up being is that it's going to be 16 over this fraction right here, which is mg. And I know it's going to look a bit messy, but hey, that's what physics is. Just a little bit messier than usual. A UK mg, right? Capital M, don't forget about that. The specificity matters, plus M. And that is your answer. Now, granted, you can get one step further and simplify this fraction by having this term multiplied with 16. But in the case of the question, which asks us to just define it in terms of given variables and gravitational constants, we already did that, so we don't need to waste time on that. Now, the question, actually, it's a C, subscript of Roman numeral 1. It says if the experiment was conducted on a frictionless surface, would the amount of time take to travel 8 meters increase, decrease, or does not change? So let's answer that. So by having no frictional force, right? By having no frictional force, what we're basically going to have as the time it takes to travel that 8 meters is this. Because what's going to happen here is that this term right here, right, the one I'm circling right now, this is frictional force. And to say that there isn't is we're going to negate that, right? So what's going to happen here is that we're going to have mg over m minus m, right, equal to time, right? Now let's think about this a little bit mathematically. If we get this number out, right, what happens is that we increase the acceleration, right? We increase the acceleration because this term is bigger than when it was subtracted with this one, right? Which makes sense. So by removing that friction, right, by having this experiment conducted in a frictionless surface, we increase acceleration. And by increased acceleration, what do we do? Well, go back to this problem. We know that if we increase the acceleration, right, the fraction or this number becomes smaller, right? In that case, time becomes smaller, right? So time becomes smaller. So the answer is that by conducting this experiment, the same experiment on a frictionless surface, what's going to happen is that the time it takes would decrease. And the question states, how much does it decrease? Well, let's I think I was going to show you the derivation, or just basically how I determine how much. So let's do that. So we already know that the acceleration it takes with the friction, of course, is this expression right here, right? 16 minus mg, that thing pretty much. And let's just call this time original, right? 0 for original. Now, the final time, right, or the time it takes for it to travel that on a smooth or frictionless surface is going to be 16. That's not a 16. 16 over, right, mg over m plus m would equal to time final, right? This is the final time, okay? Now it says here, right? It says here that shows a mathematical relationship, right? Well, let's just see. Let's show them, okay? So we know that we have two different times, right? So what I'm going to do here, is I'm going to rewrite this in such a way that I can substitute a problem in here. So what do I mean by that? Well, I'm going to show you. So, okay. Okay, I'm about to. No, I'm teaching right now. Okay, so what we're gonna do here is that we're going to try to rewrite it in such a way that this will equal to that, right? So we're going to get this m and low m to that equation. So 16, right? Remember, I'm just basically getting this m and low m times it by 16, right? I'm just doing the operation. I'm just doing the operation that you would normally do if you're trying to get rid of a complex fraction like that one. You came up with this. Right? Again, this is still, and that one is out. It's still this time initial, right? So this time I'm just going to erase it. Time initial. Time initial. And this is still, right? I can also write this as, it was 16. Write this as 16 times m plus m over mg, which equals to the time of final, right? Time of final, right? And you can see here that, it starts to get a little bit convoluted, but essentially what we can do is that we can get rid of this radical, right? We can get rid of the radical and do this. So by getting rid of the radical, what we have here is 16 m plus m over mg minus uk capital M g equal to be time initial square, right? Remember, it's the original time, right? The time with the friction, right? And again, we're going to square it on the other equation on here too. Actually, I'm just going to erase this scenario right up here. Erase this scenario right up here also. And what you're going to get is both of these equations right here. This equation is going to be time final squared, right? Now, what we could do here is that we can actually start substituting. The only way to do so is if we get this mg out of the way, right? If we get this mg out of the way, then we can start substituting. So what we can do is that we can take, yeah. So what we can do is that we can get it in terms of either mg, right? So we can multiply this here divided by here and then substitute it in there, right? Or we can find a way to, of course, get this to here. So I'm going to do this. I'll do 16 over m. 16 over m. No, there's no that. 16 over m would equal to t initial square and multiply by this denominator right here. mg minus ukmg, right? And from there, we can multiply this up here. So 16 capital M plus little m t final square mg, right? T final square mg. And you can see here that we can actually start substituting this expression in here. So instead of saying 16m plus m, we can say time final square would equal to m, no, not equal to, but time final square mg would equal to, just gonna start erasing, time final mg would equal to, I need more room than that, time final mg would equal to time final square would equal to time initial square times mg minus the frictional force, right? Frictional force with this mg minus u what the heck? Okay, that's not an m. mg. There you go. And of course, you can start simplifying even further down by saying that t final would equal to, of course, divide this in such a way where it's t initial square mg minus kmg, right, over m, and because we already taken care of that square root, what we can do is this. There you go. Is it messy? Yes, it is, but it still gets the job done, right? And actually, you can get it one step even further. If you want to, you can simplify this as the initial square mg and we can set this as two fractions instead of one entire big fraction, right? So minus to squared capital mg over mg, right? And you can see how these actually start to cancel out. This mg cancels out, this gravitational g also cancels out. So what's going to happen here is that what we're going to get is basically to squared, right? Not to, but like the initial times square minus the initial time squared times the m, the big M. That's not a big M, but I don't know why it's, there you go. Big M over M. And once again, we can also factor this as to squared 1 minus m over m would equal to the final time. Oh boy, oh boy, oh boy. Yeah, so it's like that. It's like that. That's how you can basically set that equal to the initial time. And it took a while. It took a while to do that. But yes, this is how you set that equal to the original time. So you can see here that what the initial time is going to be, I believe it's going to be smaller than that, because 1 minus whatever this is, right, whatever this is going to be, it's going to make a decimal value. So that decimal is going to make this time smaller. By making this time smaller, it's going to make this time smaller. You guys get what I'm saying, right? Because if 1 minus like a fraction, right? So x over y, right? If x over y, and if, assuming that x is greater than y, then we know that this thing is going to be less than 1. We know that for sure. It's going to be less than 1. I think, yeah, wait, hold up. Draw that wrong. It's going to be less than 1 for sure, right? And because that's going to result in a number that's going to be less than 1, then anything that's multiplied less than 1 is going to be smaller than itself, right? So because it's going to be less than 1, right? It's going to be a fraction number. It's going to be multiplied to this times squared, right? Which is going to result in a smaller number, right? Which therefore makes this time, right? Time final smaller than time initial, right? And that makes sense because the reason why is that the acceleration, if this is conducted in a frictionless surface, would be greater than the acceleration of the initial experiment with the whole frictional force thing. Yeah, and that's a doozy, but yeah, that is pretty much the expected like intuition, mathematical skill that you would need to get to do these kinds of problems. And I think that is it for today. I think we're gonna cover maybe more pulleys, ramps, definitely more ramps, but I don't think it's gonna be that hard. But yes, so expect these kinds of level of thinking and difficulty in these physics problems. And yeah, that's pretty much it. So see ya.